Hi, this is the ECE 3400 Project 2 done by Mohammad Muhi and Rohit Rajan. We'd be looking at how amplifier gain is related to device parameters for fundamental MOSFET circuits. First, we take a look at the common source MOSFET amplifiers. Considering figure 1a, we see that the MOSFET is connected to an ideal current source, which causes the gain to be affected by the sigma n of the MOSFET only. Also, looking at the relationship between gain and bias current inside the subthreshold region, we see that they are completely independent of each other as given by the above equation. But analyzing this relationship in the above threshold region, we need to consider a small signal model which causes the gain to depend on the bias current as follows. If we were to use a PFET to model an ideal current source, we see that the gain in fact drops due to it being affected by the sigma of the NFET and the PFET respectively. Some design changes we need to consider to increase amplification is to increase kappa or decrease sigma n or sigma p. Using the slope of the curve fit, we see that the gain is negative 458.71. Using values from our previous project though, gives us a negative 319.51 gain. Using multisim and the PFET and NFET values we got from our previous project, we see that the data and the simulation do agree with each other. The project required us to run the simulations at a 5 volt VDD while the experiment data is seen to be run at 3 volts VDD.
Now we are going to talk about differential pair amplifiers. Some of the preliminary questions that we had for the differential pair amplifier was, if we assume that the current source is being biased, then is it sufficient to assume that all MOSFETs in the subthreshold region for the other current source amplifier, are they going to be in subthreshold too? It is true, because I1 and I2 are both subthreshold because of IB, which is already being in subthreshold region, and they're both components of IB. And the minimum drain to source voltage is going to be equal to the fixed voltage, which is V tau plus 4 UT, the thermal voltage. For the derivation of the currents for the differential pair amplifiers, we have I bias equals I1 plus I2, and I1 is e to the kappa V1 minus VTO minus Vx divided by UT. It's the same thing as I2, except instead of V1 you have V2, and VTO is going to be the threshold voltage, and Vx is going to be the input voltage. And I1, it's going to, and we manipulate I1 and I2, and as we could see from the next slide, in here, that after more manipulations, we finally arrive to I1 and I2, where I1 is equals to IB, I1 equals to IB divided by 1 plus e to the kappa V2 minus V1 divided by UT. I2 is similar to that, which is IB divided by 1 plus e to the kappa V1 minus V2 divided by 2. Basically, they just shifted positions. For this case, for V2 significantly greater than V1, we see that I1 is I ref divided by 1 plus e to the kappa V2 divided by UT. I2 is going to be similar to that, except the V2 is going to be negative V2 because of the V1 term is the beginning of it, and it's going to drop out. We simulated a differential pair amplifier circuit in multisim, and as you see here, it's going to be swept in V1, and V2 is going to be kept as 2 volts, and we made our VB, our bias voltage, to be 0.2 volts. For the differential pair amplifier, we obtained the experimental data that was given to us, and we plotted here. The green one is I2, and the yellow plot is I1, and the red maroon is the I1 plus I2, which is I bias, and the blue curved line is I1 minus I2. And as you can see, I bias is measured to be 8.1 nanoamps. For the differential pair amplifier experimental data, we have normalized the current value by the log function to perform the curve fit. For the curve fitting, we took a linear region for the two specific I1 and I2, and we found this linear slope for it. The slope is equal to kappa divided by UT. And the first slope was the blue dotted line, which is 26.8, and we figured out kappa 1 to be 0.694 volt, 0.694 volts. And kappa 2 is times divided by UT, it's going to be 27.44. And we extrapolated them and found that kappa 2 was equal to 0.711. And here we did the differential pair amplifier simulation for the multisim, and we see that these are very close to the value that we had for the experimental data. As also seen the differential pair amplifier, the log current plot, it is very similar to what we had for the experimental data too, and these simulations match up pretty well with our circuit. For the transconductor amplifier, this is the multi-sim circuit design we have. We set the VB to be 0.25 volts and V1 and V2 to be 0 and 2 volts respectively. In here we have plotted the output current versus input voltage for the transconductor amplifier with both simulated and experimental data. And as you see here, they both have the same shape. For the simulated data, it is shifted a tad bit down and tad bit to the right, the simulated. From the experimental value. This could be maybe counted by the I offset from the output current, because I offset is a pretty significant figure. If I offset is changing a little, that means I output is going to change a lot. The first parameter that we're going to measure for the transconductance amplifier is going to be measured voltage gain, which is going to be VR divided by Vin. And in this plot, we're going to take the linear region of this set of data, and it was found to be 329. For the transconductor amplifier, the second parameter we're going to measure is the output resistance, which is going to be calculated by V out divided by I out. And in here, we found that to be 3.67 gigaohms. For this third parameter, we found that it's going to be transconductor amplifier, it's going to be transconductor measurement, which is going to be I out divided by Vn. And for this plot, when we saw this, after we do this linear interpolation, we saw that it's going to be 83.5 nanosiemens. And overall, we saw that for the transconductor amplifier, the gain is going to be 329, output resistance is going to be 3.67 gigaohms, and our transconductor is going to be 83.5 nanosiemens. And our calculated gain is going to be transconductance times output resistance, which is going to be 306.445. And the calculated gain was 6.85% error from measured gain, which is pretty good. Thank you for listening to ECE 3400, our project 2.